Howdy, ladies and gentlemen. You see a smile on my face because we are back at a new semester of information. Not only is it a new semester, but it is the second semester. Halfway there. All right. Now, as I've been telling a few of the students as they've been coming in to get materials, which I hope each and every one of you has had an opportunity. If not, I'll be uploading PDF versions of the notes and all the stuff you would normally get at the beginning of each chapter, along with the video. So make sure you get what you need because you're going to need them right off the bat. Anyway, as I've been saying all along last semester and to those few students that I've seen so far today, is second semester, they always say, is it easier? And I say, yeah, it's easier, but it's all relative because Chapter 5 is one of the last chapters that we're going to see a decent amount of math. Okay, nothing too crazy, but we are going to have some math in this chapter. Okay, Chapter 6 has a little bit of math, not a whole lot at all. And then 7, 8, and 9, really none whatsoever. Like no math at all. Chapter 10, if we get there, that gets into math. But what's nice about Chapter 10 is it is basically all formula based. So you just plug in numbers and then you're good to go. All right. But again, like I said, it's all relative. So keep that in mind. But yes, we typically see we change pace a little bit in the second semester in terms of the topics and what goes into those topics. So you can all pretty much sigh a breath of relief because math's going to be put to the back burner for the most part after Chapter 5. But until then, we have to do Chapter 5. And Chapter 5 is all about thermochemistry. And I really hope that we have an opportunity to do the lab for this chapter, because this is the chapter where we get to burn stuff. We get to burn food, and we get to see how much energy is in that food that we burned through a process of what's called calorimetry. And it gives you an insight into the amount of energy that foods can provide you as you eat them. So you can kind of see how it intertwines with the human body. But I always enjoy starting off Chapter 5 with this quote. Thermodynamics is a funny subject. The first time you go through it, you don't understand it at all. The second time you go through it, you think you understand it, except for maybe one or two small points. The third time you go through it, you know you don't understand it, but by then you are so used to it, it doesn't really bother you anymore. Thank you, Mr. Arnold Sommerfeld. It's not that bad, okay? It's just a funny statement to kind of get you thinking about thermodynamics itself. Speaking of thinking about it, look at the name thermodynamics. Get an idea of what you think we're going to be discussing in this chapter, okay? You have thermo, you've got dynamics when you break it apart. So thermo, you might think of heat, okay, which you would not be incorrect. In fact, heat really is just another form of energy. So really what we're going to be looking at is energy. And then we see dynamics. And so you're going to see how energy is going to be moving in and out throughout various systems. And that's what we're really going to be talking about, is the flow of energy. Okay. So we're going to start talking off about energy itself in this first section. Okay. There are numerous definitions that we can attribute to the word energy. Okay. Whether it be our everyday uses or, more importantly, in this class, the scientific definitions. Okay. And that's what we're going to stick with here. Energy is the ability to do work or transfer heat. All right. So an energy must cause an object that has some mass to move a non-specified distance. That's what we call work. So energy is used to move an object that has mass some distance. Okay. It doesn't matter if it's a centimeter or a mile. Okay. As long as it moves, then work has been done on the object. Energy used to cause a temperature of an object to rise is called heat. Okay. So we've got heat, we've got work. We're eventually going to see how these two fit together in certain scenarios a few sections down the road here. But that's really our main definition of energy, okay? You should know hopefully you should know from your intro to chem phys days or maybe some other class, there are numerous types of energies, and there are some very common ones like kinetic energy, okay? Kinetic energy is the energy an object possesses by virtue of its motion, okay? So we have this formula of E with the sub K here, okay, because it stands for kinetic energy, is equal to 1/2 times mass times the speed squared. So only the speed is squared in this one, okay? So we're going to be talking about kinetic energy, and its counterpart really is going to be potential energy, okay? We can see potential energy in various situations. It's an energy of an object possesses by virtue of its position or chemical composition, okay? The most important form of potential energy in molecules is what's called electrostatic potential energy, or E sub EL, okay? And really, you've got this formula here. We don't necessarily need to know or solve what this formula is, but I do want to call to your attention, how we can use it without necessarily calculating anything, okay? So K is a constant. We're going to see this formula later on down the road here. We're going to readdress it. But K is a constant, okay? We don't necessarily have to worry about that. We have Q1, Q2 all over D, okay? Q1 and Q2 are, in terms of molecular arenas, is the charges of one particle and another particle, Q1, Q2, okay? The denominator, D here, is the distance that they are from each other, okay? So as you can see here, we can have a larger electrostatic potential energy if we have larger charges on either of the molecules. We can also have a smaller electrostatic potential energy between molecules if the distance is large, okay? So you have to start being able to take a formula and make rationalizations based off of just the formula setup itself, all right? We don't necessarily have to have any calculations involved, but start getting an idea of like, okay, if we have large charges and small distances, we're going to have high electrostatic potential energy. Sorry, there's a little gnat. If we have small charges with large distance between them, they're going to have small electrostatic potential energy, okay? So we're going to come back to this, as I mentioned, a little bit later on, okay? So when we are talking about units of energy, energy is in joules, capital J, where 1 joule has the subunits that makes up a joule of kilogram times meters squared per second squared. Sorry, I couldn't really do a very good job of writing this in here. Sometimes when I go from my Chromebook to my computer, the formatting gets all wonky and it doesn't look right. So apologize for that. So really it's just 1 joule is equal to 1 kilogram times meter squared over second squared, okay? A unit that we used to use, but we no longer really use it, but a lot of old school scientists still use this. It's called the calorie, okay? There are 2 calories. There's this calorie, which has a lowercase c, and you see that it has a conversion of 1 calorie is equal to 4.184 joules. There's also calorie, but the C in calorie is capitalized. That's the food calories that we see. And yes, there is a tie-in between this calorie and the food calorie that has a capital C. And when we do our lab, you're going to see how that ties in. You'll see it some other time too. But there is a connection between all 3 units, okay? So we're going to be coming into this at some point in this chapter. Next thing we have to define is what's called the system and what is called the surroundings, okay? Because we need to be thinking about this when we start talking about changes in energy, okay? Here we have a cylinder with a piston in there, and we have hydrogen and oxygen molecules inside of here, okay? In this particular system, matter cannot enter or leave the system. Everything is confined to this space right here. Energy, though, can enter or leave system as heat or as work done on the piston. Okay, so we have the system, which includes the molecules we want to study. So in this case, the system, the object that we want to study, are the hydrogen and oxygen molecules. The surroundings are basically everything else. The cylinder, the piston, anything that's really going to be interacting with the system. Okay. Again, system surroundings, we'll come back to that. We're just getting a real quick glimpse into some of the topics we're going to be discussing throughout this chapter. So we will be coming back. Next, we have work. We already saw one of the first slides of this video, work, okay, and how energy is related to work. Again, energy is used to move an object some distance. So work can be calculated by taking the force and multiplying it by the distance that's traveled. Now, we can also determine what force is. If we're not given force directly, and our force is going to be measured in newtons, if we're not given force directly, we could take the mass of the object and multiply it by the acceleration due to gravity, which is 9.81 meters per second squared. Mass times gravity gives us force. So there are ways that we can calculate objects or units, even if we're not given them directly. Okay, but we have to have the right pieces in order to do so. Heat is a very big topic that we're going to talk about in this chapter. We can transfer energy in the form of heat. If we look at the example over here on the left, we have the burner, which has fire coming out of the burner. It's transferring heat to the water to make the water's temperature rise. As the liquid water rises and gets closer to a certain level, certain temperature, we're going to start seeing the bonds start to break that keep the liquid water molecules together, and we start to see the formation of steam. Now, there's a very important rule. Heat was going to flow from objects that are warmer to objects that are cooler. That's what's happening when, especially at this time of the year, when it is wintertime out and there's snow or ice or anything cold that you grab, your hands are warmer than that cold object. It's warmer than the snow, it's warmer than the ice. So what's happening is the heat from your hand is being transferred or is flowing from your hand to the cooler object. A lot of times it's really about equilibrium, okay? But that's why your hand begins to feel cold. It's because you're losing heat to the colder object. So we have some rules that we have to follow in the chemical and physical world, and that is we can neither create nor destroy energy. All we can really do is convert it from one form to another. And we've only just touched the surface on the forms of energy right now. We've talked about kinetic and potential, and there's others, okay? Energy can be converted from one to the other and back and forth and back and forth. We see this with roller coasters, where we go from potential to kinetic and back and forth, just depending on where the roller coaster train is located in the whole process. As we see this cyclist sitting at top of the hill on the left-hand side. Cyclist is sitting high in relation to the bottom of that hill. So the bicyclist at the left has high potential energy, but she is stopped. And so since the bicyclist is stopped, she has zero kinetic energy because she's not moving, okay? But she does have high potential energy. As she begins to descend down the hill, okay, first of all, she's increasing her movement, so therefore she's increasing her kinetic energy. But at the same time, as her height in relation to the bottom of the hill decreases, her potential energy is going to be decreasing. So again, start off with high potential energy, zero kinetic, go down the hill, they start to flip-flop. They start to be converted from to higher kinetic energy and lower potential energy. And again, as we just mentioned, this is just explaining it a little more. Okay, so now what we're going to be doing is taking some scenarios. We're going to be calculating work. We're going to be calculating kinetic energy. All right, so Let's look at our example here before we get into our practice exercise here. So here we have a bowler. This bowler is going to lift a 5.4 kilogram bowling ball from the ground level to a height of 1.6 meters. The bowler then drops the bowling ball. Three-part question here. A asks us what happens to the potential energy of the ball as it is raised. B asks what quantity of work in joules is used to raise the ball. And C, after the ball is dropped, it gains kinetic energy. If all of the work done in part B has been converted to kinetic energy by the time that the ball strikes the ground, what is the ball's speed just before it hits the ground? Okay, so let's address A. What's happening to the potential energy as the ball is being raised? Well, we are taking that ball as it sits on the ground and raising it up 1.6 meters. So now, from the point where the ball is raised to the floor, I have increased my distance, increased my height. So, thinking about that, we should answer this question by saying that the potential energy relative to the ground increases. Okay, I have a much larger separation in terms of height as I raised it to 1.6 meters. So that is A. Potential energy is going to increase. Part B says, what quantity of work in joules is used to raise the ball? Okay, so again, work, as we saw a few slides ago, is equal to force times distance. But we are not told directly, as I mentioned a few slides ago, what the force is. We don't have any force in newtons. Listen to us. But what we do know is we do know the mass of the bowling ball in 5.4 kilograms, and we do know the acceleration because we're here on Earth is 9.8. They use 9.8. If you use 9.81, it won't make that big of a deal. But 9.8 meters per second squared. So we could take the mass of the bowling ball, the acceleration due to gravity, multiply those two to get our force in newtons. Then we take that force in newtons and multiply by the distance that the ball was raised, 1.6 meters. So, as you see here, when we do all that, we get 85 kilograms. Now, this is not minus, okay? This is not kilograms minus meters squared per second squared. That should be like a multiplication dot, or like even put an X there to indicate multiplication. But it should be 85 kilograms times meters squared per second squared, which really, those combination of units equals joules. So make sure you answer it in joules, okay? I really don't want to have to take off points, even when you get this far, if you don't correctly answer it in joules, okay? So there are 85 joules of work done on the bowling ball. Last question. After the ball is dropped, it gains kinetic energy. If all the work done in part B has been converted to kinetic energy by the time the ball strikes the ground, what's the ball's speed just before it hits the ground? Okay, so a couple things we need to take note of is we know that, or we are told that all the work done in part B is converted into kinetic energy. So we know that if we took the formula for kinetic energy of EK is equal to 1/2 mv squared, that these values here should be equivalent to 85 joules, because we said all the work done was converted to kinetic energy. But what we need to figure out is the speed just as it hits the ground. So we have to take this equation right here. Okay, I almost tried to cover up something on my screen and realize that you're not going to be able to see that. We're going to take this 85 joules equal to 1/2 mv squared and rearrange it to solve for V. And so if we take our generic kinetic energy formula of EK is equal to 1/2 mv squared and rearrange it to solve for speed, we're going to get this, okay? We're going to have V squared is equal to 2, which comes from the 1/2, EK over M. So we plug in our values here. Again, our EK was 85 joules. As you see here, they broke it down into its smaller components so it could cross out anything that needed to be crossed out so we get the appropriate units that remain. And you'll see that we have 31.5 meters squared per second squared. But those are not the correct units. Meters squared per second squared is not the correct units for speed. One thing we can't forget, we have that little square there, v squared, okay? We are only wanting to solve for v, not v squared. So we have to get rid of that square. And in order to get rid of that square, we have to square root both sides. So we get v is equal to the square root of 31.5 m squared per s squared. And we get a final answer of 5.6 meters per second. Okay? And rewatch part C a couple times just to see if you grasp it after the second or third time here. All right. Now let's look at the practice question here. Okay? So it is a two-parter. All right? Let's look at one at a time. And I'm not going to lie. There is a way that we can solve these questions using this hint here. Okay, 1 AMU is equal to 1.66 times 10 to the negative 27th kilograms. But in order to use that hint, we kind of you'd have to go in a direction and use stuff that we really haven't talked about this year. So I tend to ignore that hint every time I discuss this question. Instead, I like to go through a process that we should be familiar with, all right? Whether we be rusty at it or not, that leaves us to be determined for a later date. But at least we should be familiar with it to some extent. So let's do part A first. We are to calculate the kinetic energy in joules of an argon atom moving at a speed of 650 meters per second. Okay, so 650 meters per second, a single argon atom. Well, how do we figure out what a single argon atom weighs? Or what mass does a single argon atom have? That's where we get to our trusty periodic table that I forgot to grab before doing this here. Okay, here we go. All right. So I'm going to get into this. All right. Going to dim the light a little bit. All right. You guys excited to hear that bell noise? Oh, just another week. All right. Argon. You can't see that. It needs to be zoomed in. Okay. Argon, right here, number 18, has an atomic mass of 39.948 AMU. We could also say 40 for ease of calculation, because really the difference is pretty small. So we'll just say 40, okay? Now, we're dealing with moles, okay? If you look at part B, it talks about moles. And we know that the values, the atomic masses listed on the periodic table are also equivalent to the molar mass, okay? So if we look at the periodic table, we see that there are 40 grams per mole for the argon molar mass. Okay? So, we got a couple of things we have to do. First off, we have to determine what the mass of a single atom of argon is. Then we have to determine, how many, then we have to convert that into kilograms, because we have to have our mass in kilograms for our calculation here. So let's start off small, okay? So we have 40 grams per mole. And if you can remember how many atoms of anything, or of any element, there are in a single mole, okay? We have Avogadro's amount of atoms in a single mole. 6.022 times 10 to the 23rd atoms. So that allows for our moles to cancel. And so then we solve this and we get an answer of 6.64 times, 10 to the negative 23 grams per atom. Okay? So this is how many grams a single atom of argon weighs. But again, we can't use grams in our calculation. Okay? If we're trying to calculate the kinetic energy, we have to have it in kilograms because kilograms is a unit in joules. So I'm going to take what I got over here, 6.64 times 10 to the negative 23 grams, and multiply it by 1 kilogram is equal to 1,000 grams. This allows for grams to cancel out. And so this is a very important step. If you are using scientific notation in these types of calculations, make sure you put everything in parentheses. Otherwise, your calculator is not going to like you. Okay. This can also be written as 10 to the third. Okay. That equals 10 to the third, 1,000 grams. So I go ahead and do this, and I get 6.64 times 10 to the negative 26th kilogram per atom. So this is the number in unit that I'm going to use for my calculation. I can finally, now that I've got everything converted, I can finally solve this. I get 1/2 times my mass of 6.64 times 10 to the negative 26th kilogram times its speed squared, which was 650 meters per second squared. So if you want to put this in your calculator before I solve this, you can pause the video. But once you've done this, you should get a final answer of 1.4 times 10 to the negative 20th joule. So this is how much energy a single atom of argon contains when it is traveling at 650 meters per second. Not a whole lot. But let's compare this answer, since this is just one, let's compare it to a whole mole's worth. Okay? That's part B. See, part B says, a mole of argon atoms traveling at that same speed. So, again, if we have a mole, we don't really have to do any conversions. We just have to make sure that we utilize the mass in kilograms that we did in part A. So, since we're not determining the mass of a single atom, we can just use the molar mass as indicated on the periodic table, just convert the grams to kilograms. So we have 1/2, 0.04. Did I do that right? Double check. Yep. Okay, so the mass of a mole in kilograms of argon times the speed it's traveling squared. Yet if you want to solve this on your own before you check your answer, you can. But you'll get 8.4 times 10 to the third joules. So it's quite the contrast in terms of kinetic energy between a single atom and a mole's worth of atom. That's a big amount of energy. One atom, not so much. So a few things to take away from this is when you're calculating kinetic energy, you must have the mass in kilograms. Okay? If you are calculating for speed, okay, where you're going to have this situation, okay, you cannot have v squared is equal to, you must square root, okay? So you must square root and get this. So keep that in mind whenever you're doing this. So there you have it. That is section 1. We're going to be going through about 4 sections in this first week, okay? Now, pay careful attention to my plan book. I'll be making announcements as well. But we will be having a quiz over sections 1 through 3 on Monday, January 11th. Okay, so make sure you pay attention to any postings, okay? And if you happen to be watching this video in the future, pay careful attention to the date that I just said, because it may be different when you're watching this. All right, folks, that wraps up section 1. If you have any questions, email me or message me. But I will be posting this video along with the other materials, so make sure you get a hold of them. Have a good day, everybody.